Welcome everybody to our webinar today. This is a webinar focused on using the Elios 3 drone in nuclear inspections and radiation detection. So I'm your moderator for today. My name's Eloise Muckman-Mitchell, and I'll be joined today by Jeff from the Flyability team, as well as Kevin from the Idaho Environmental Coalition. Just a few notes about how the webinar will work. So if you'd like to ask a question during a webinar, you've got this panel on the side where you can type in your questions. I'll see if the video works, but it doesn't always cooperate. Good, today it does. So you can ask questions there and we'll see your questions. They're not going to pop up during the webinar and none of the other attendees can see them. So we'll just get them on the organizer side and answer as many of them as we can towards the end of the session. If we can't answer them all, we'll get back to you via email and hopefully answer your questions there. This webinar is being recorded and you'll receive a replay afterwards, so you can revisit all the wonderful ideas that we're going to share with you. So this is our overview for today. We're going to teach you a bit about the Elios 3 as well as Flyability as a whole. So for those of you who don't know us already, you can get to know us. And then we'll be going into detail of kind of what the Elios 3 drone is and the RAD payload, and Jeff will help give us some more technical details there. And then we'll hand over to Kevin, who's got lots and lots of insight into how he's been working with the Elios 3 RAD and an interesting case study about its applications. So to get started with Flyability. So Flyability is a specialized drone creator based in Switzerland. We were founded back in 2014 and we've grown significantly since then. We now have 4 international offices around the world. We've been developing drones in that time with one singular aim in mind, and that is to have drones and technology capable of doing dangerous jobs so we have no more humans at risk. And through this, we're creating specialized inspection drones that can be sent into confined spaces or complex environments that through doing that, those spaces don't need to be gone into by humans, or at least when we go into them, we have much more situational awareness and idea of what we're going up against. And so with that in mind, our flagship at the moment is the Elios 3. This drone was released last year and it's unique in the world and we think it's pretty great. So it's the only cage drone currently that carries a LiDAR sensor, and it has a specialized modular design that enables it to be tailored for specific industries. For instance, for those of you interested in RAD, it has a specialized RAD payload, which Jeff will tell you more about. And with this design, it means that the Elios 3 can be specifically used in different sectors according to their specific needs. This drone does help us to accomplish our mission of keeping people out of harm's way. It's very well designed in terms of its structure, so that it's got a special cage for helping it be collision tolerant, in addition to its camera, which you can see just here at the front in red, and that's a 4K video camera, in addition to the big lighting system that helps it navigate tough environments where it can't see very much, plus the LiDAR sensor. And then to give you a bit more of a breakdown of the Elios 3 RAD itself, I'm going to hand over to Jeff. Are you here, Jeff?
Yep, hello everyone. So to build on top of the amazing Elios 3 that Eloise just presented, we thought this drone really as a platform onto which we can add software, we can add payload for tailored applications. And the first payload we are released is a RAD sensor. And we partnered with Mirion Technology, which is a leader in the RAD sensing space. And we use their main sensors to be coupled with the drone. And it gives us the ability to couple the Elios 3 amazing flight capabilities and data localization with the radiation sensing capabilities of the Mirion sensor. So if you go to the next slide, basically we are basing our product on the RDS-32, which is top in class in terms of radiation sensing, used quite a lot in the industry. And we also can deliver a wide range of measurements from microsieverts up to 10 sieverts per hour, so that you can cover a lot of use cases with a single device. And as we know that having a qualified and certified sensor is really important for customers in the nuclear industry, we did little to no change on the sensor itself. So you could use the off-the-shelf RDS32 that you have, add a little bit of configuration to be compatible with our drone. Yeah, so on to the next slide. I guess that's for you.
Yeah, it is. So basically a bit about the Elios 3 RAD in numbers. So already over 80% of nuclear reactors in the US have flyability technology on site. And one of the great things about using the Elios 3 RAD is the ability it has in withstanding these sort of tough environments. So we've had lots of rigorous testing in order to test just how much the drone can take in some of the more extreme scenarios. And we've seen testers and clients have major savings, and a lot of that comes from having the correct data and situational awareness to deal with being in these tough environments and gathering data that can then inform engineering plans, maintenance, inspection, etc. So then going into what to expect with the Elios 3 RAD, I think Jeff has a better idea of this than I.
Yeah, indeed. So as you know, Elios 3 is equipped with a lidar and is able to produce really precise maps, and this allows data localization. And this, coupled with the radiation measurements, we can colorize the trajectory of the drone with the measurement we take, and this allows to precisely position and locate where radiation sources might be. And also, thanks to the amazing stability of the drone, we can really go close to the source, get in contact, and stay as long as we want to get a precise measurement. And this helps, of course, for about detecting and finding all sources. It allows users to plan their different work by doing their survey without sending radio protection in, for instance, and know how much those humans will be exposed, as well as doing this kind of survey and monitoring while the plant is in operation, which can be a huge cost saving for a nuclear power plant. And also the drone is constantly measuring its own cumulative dose. And so you can monitor how much dose you saved by using a drone instead of a human. Yeah, so another points on data localization, you can get access to this information directly live using the drone, as well as on our post-processing software, as you can see a screenshot on the right here. And I think Kevin will be going a bit more in details with concrete examples.
Great, thank you very much, Jeff. So now we're going to hand over to the wonderful Kevin Young, who's going to tell us about the Elios 3 and Elios 3 RAD. So we're going to switch over to Kevin as your presenter. And so that should go through in a second. Great. Kevin, I can't hear you. I don't know if you're still on mute or anything.
Am I coming through now?
Yes, you are.
Can you hear me? Okay, great.
Yes,
great.
But can't see you.
Oh, let's see if we can share a webcam. How about that? That might help.
Great. Thanks very much, Kevin.
You bet. No, yes, thank you, Eloise, Jeff, for allowing me to be here and talk to everybody out there about our use of the Elios drone in the nuclear waste remediation industry. My name is Kevin Young. I am the lead engineer for indoor drone inspections with the Idaho Environmental Coalition. We're a prime contractor to the United States Department of Energy, and we're involved with their multi-billion-dollar nuclear cleanup effort across the United States. And this is an industry where this new tool of the indoor inspection drone is showing immediate benefit. And that's really where we started adopting this tool, was as soon as it was available and proven to be practical. Not only our company here in Idaho, where we're cleaning up sites in Idaho at the Idaho National Lab, but across the US DOE complex sites, we're seeing that this indoor inspection drone tool is going to provide a significant benefit to help reduce cost and increase worker safety. So it's all about reducing hazardous work hours for humans. And if we reduce the number of hazardous work hours by allowing a indoor inspection drone to do the work for us, then that is a direct correlation to increased worker safety, which leads very much to reduced project cost. So adopting the drone was pretty much a given as soon as it was available. So one of the things I want to do is present a case study that was our very first use of the Elios 3 for LiDAR mapping, as well as the Elios RAD payload. And I'll just briefly cover the problem that we were facing, and of course the solution, and share a few of the results. We'll conclude with a summary of the benefits, perhaps discuss a few of the lessons learned. So the best thing I can do for this case study, to give you some visual context for the rest of the next 10 minutes or so, is to show you a highlights video of the day of the mission. So you will see video of the Elios 3 collecting LiDAR data, and you'll then be able to use those visual images as we go through the remainder of the slides, and hopefully have a better understanding of the content. So let me go ahead and kick this quick video off. This is about a minute long. And this mission occurred in November of 2022 out at Idaho. It was very cold that morning. It was about 16 degrees Fahrenheit. And so we were concerned, of course, with batteries, but we took measures to keep the batteries warm prior to use. And here it is, the Elios is entering into this storage vault that contains large bins holding radioactive material, waste material. And the goal is to create a LiDAR map of the interior that we would use later to install equipment for remote removal of the radioactive powder inside these large bins. So we did, we'll talk more about this, but we did 2 flights collecting LiDAR. We did a 3rd flight where we attached the Mirion RDS-32 dosimeter payload and collected some radiation readings, which once again, I'll go into a little more detail on that, since this webinar is focused on the radiation. We took measures to protect the drone, or to encase the drone when it came out of the vault, just in case it by chance had any radioactive contamination, which it did not. The radioactive powder had remained well within the bins. But the 3D map generated from the LiDAR data was exceptional. We were very happy with those results, as well as the radiation readings that we received. So as I mentioned, we were doing 2 things on this day. The primary mission, the most important mission to us, was actually collecting the LiDAR data to generate a 3D map. The equipment we have to install to remotely access, cut into the bins, and retrieve the radioactive material has to be placed precisely among all of the obstacles that are above that bin, whether it's the vent and fill lines, the electrical conduits, pipe hangers. There's plenty of obstructions there that we had to know precisely where all that equipment was. And getting into that vault, which had a very high radiation level, as well as limited access, made it a perfect candidate for using an indoor inspection drone. So collecting the LiDAR, primary mission. If that was successful, our management had given us the go-ahead to do a third flight or an additional flight to collect the radiation levels inside that vault. Previous to the mission, we had radiation readings, but they were collected in a way where the engineers were, there was some margin of error, and we wanted to confirm precisely what the actual radiation readings were. So I'll talk more about that as we go. That mission, the secondary mission, was what we call partially successful. There was an issue where we could not retrieve the drone on that third flight, and it's still in the vault. And as of today, it has roughly, what is that, 52,000 gray of a cumulative dose and counting. Hopefully, if we get it out of the vault someday, it will be a great material study to see how the radiation affects the materials on the drone. And there is a chance that we may be able to retrieve it in the future. Okay, so let me give you a rundown on exactly what where the Idaho National Laboratory site is. It is in the state of Idaho, and we are one of several Department of Energy nuclear laboratory sites. And so Southeast Idaho is where we're located. And on this site, more specifically, we have what's called the calcined solid storage facility. That is what you saw in the video. That is considered the storage facility for this calcined material, which is a byproduct from the reduction of liquid waste, which was used to reprocess spent nuclear fuel. So essentially, they evaporated the water and had this powder remaining. Once again, give you a little bit of perspective, the bins themselves are actually stored in an underground vault, concrete vault that was built way back in the 1960s. So there's an image showing below ground how those bins are stored in the vault. There are 4 bins and approximately 220 cubic meters of granular waste, radioactive granular waste. And our goal was to map the obstacles above the bin within the concrete vault, because that's where we need to remotely place the retrieval equipment to extricate the powder and remove it from the bin. By the way, the reason we're removing the powder is it's an agreement between the state of Idaho and the United States Department of Energy that the US DOE would remove all nuclear waste from the state of Idaho by, I believe, the agreement date is 2035. All right, so this mission has challenges. First and foremost, when the radioactive material was placed into the bins back in the early 60s, it was never intended to be removed. That was before the settlement agreement. And so they did not design any measures for easily getting into the vault and retrieving the material. The only entry into the vault is a single 56 centimeter square hatch in the roof of the vault, which this dotted red outline kind of shows you where that opening is. And if you're trying to collect LiDAR data from inside a complete LiDAR map inside this roughly 13 meter square concrete vault, you have to have a way to get your LiDAR device roughly in the 4 corners of the vault to make sure you're getting full coverage. So once again, the indoor inspection drone with LiDAR was a prime candidate. As I mentioned, the 56 centimeter square vault. Luckily, the Elios 3 drone is roughly 48 centimeter diameter in the horizontal, which gave us a little bit of margin for our pilot to lower that drone, fly that drone in. Significant radiation in the vault. This was estimated to be 10 to 20 gray per hour gamma, and high temperature due to the radioactive decay, significant dust, multiple obstructions. All the things that the Elios 3 is really good at handling. These were the capabilities that were very important to us in order of importance. So the size, the protective cage, the fact that it has a LiDAR sensor on it, and the dosimeter, very important. We also really were happy to be able to get really good quality video from inside the vault. The oblique lighting helped in the dust, and then the remote antenna option helped us get the signal out. So when we chose to go with the Elios 3, it was actually back in April of 2021. The mission was not until November of 2022. We had to go through several tests to ensure that the drone would perform. One of them was first was a maneuverability test in October of 21. It passed that test with flying colors. The cage is a critical part of being able to maneuver in very densely obstructed areas. In June of 2022, the key test was a radiation tolerance test. We were estimating, as I said, we estimated it may be as high as 20 gray per hour in the vault. We did some radiation testing in front of a high-powered X-ray generator, and the Elios 3 actually survived and flew successfully in a 100 gray per hour field, and was able to continue operating up to 40 gray of cumulative dose before we had a failure. And that failure mode was actually the onboard computer memory chip. The dosimeter performance testing back in November 2022, this was important because at the time, the RAD payload was still in a prototype stage. And you might be able to see on the right, person looking at the control console, person on the very left, that's actually Jeff there. He came out and gave us a demo of the RAD payload. We flew it over a cesium check source, and the system performed well. Here's a quick video too of us, our pilots, performing a test flight with the RAD payload on board. We simulated the vault, the hatch openings, and this allowed our pilots to practice flying the maneuvers. You can see on the floor of the high bay below the taped outlines of the 4 bins. This gave the pilots the opportunity to fly and collect the data as they, or get to the data collection points as quickly as possible. And so the mission itself went very well on 16 November. We did 2 flights of LiDAR, about 6.5 minutes each. We did have the Flyability and GeoSlam software experts on site in our control room just to make sure if we had any issues with this flight, we had experts right there on hand. This flight was actually a first for the US DOE to fly an indoor inspection drone within a very high radiation vault area. We did a quick data look after each flight, and on the 3rd flight where we attached the RAD sensor, the drone did fail to exit the vault, and we are pretty sure it was most likely due to a rapidly increasing air temperature inside the vault. It was so cold that morning when we first opened the vault, cool air rushed in, but throughout the course of the 2 LiDAR flights, we were pretty sure the air inside the vault was heating up to the point where it exceeded the ability with the added weight of the drone, or with the added weight of the RAD payload, to maintain lift. The safety analysis indicated that there was no issue to human safety or the integrity of the storage bins to leave that drone down there. And the good news is we were able to successfully transmit out the radiation readings, which gave our RAD engineers a very solid understanding of what those radiation levels were inside the vault. I do want to give you a quick video of that third flight, and this is from the POV of the pilot. And you'll see the RAD widget down here. I blow it up occasionally. This is at 21 microsieverts right there. And it's doing its initial flight. You can see it has no problem flying with the RAD payload at this point, where it's much cooler outside the bin. And you're going to see the RAD levels start to increase in the lower left as soon as you get over that opening and you're getting the shine from the radiation coming off of the bins. As it's entering the vault, we're at approximately 11 millisievert per hour right there. Right before it enters the lower hatch into the bin proper, I believe we're reading roughly 35 millisievert, or 350 millisievert. And once it drops into the bin, and you're seeing there's a little buffeting, a little bit of airflow from the hot air rushing up out of that hatch opening. At this point, our pilot's looking over at me and saying, I cannot maintain lift. And the drone just slowly lowers down to the top of a bin group number 1, where all attempts to get the drone to fly again or to achieve lift and get out of the vault failed until the battery died. Now we did get a final reading of 7 sievert per hour at the bin top, and that in itself was an amazing bit of data, because our original estimate said that it could be as high as 20 sievert or 20 gray per hour. And the fact that it's only roughly a third meant a huge savings for us in how we design the retrieval equipment and how we do our operations. So, let's see. Let me back up on that one. Anyway, we'll say that the LiDAR data collection was great. We got a very comprehensive, complete map, a 3D map based off of the LiDAR data using GeoSLAM software. The radiation data was transmitted out of the bin. We were able to generate this radiation profile that you see now. And as I said, only 7 gray per hour versus 20 gray expected, which was a huge plus for us. In conclusion, I just want to say that the ability for the Elios 3 to operate in a radiation environment exceeded our expectation and was by far much more capable than what we required for this initial mission. Now, we would like to see more testing to increase the confidence on these survivability numbers. The primary mission that we collected, the LiDAR data, was a complete success. The 3D map above the bin top was very much critical for us to achieve program success in installing our remediation equipment. And the secondary mission of the radiation data collection provided valuable radiation levels, which, as I mentioned earlier, will support our design in terms of the amount of shielding required. It will help us plan our operations based on how long we will allow operators to work above that area. And all of that is based on the information, the data that Elios 3 was able to collect for us. And that's pretty much it. I hope we have time for questions and answers. I think there may be some questions out there.
Yes, we have plenty of time for that, Kevin. Thank you. Actually, if we could go back to some of your early slides, I had some questions about going into more detail about some of the photos you showed.
Sure. Which one would you like to see?
I think it was in your intro slides. You had basically a slide with 4 photos on it, and it was just a question about what we were seeing.
Oh, right. I'm sorry. Yeah, I could have done a little bit describing that. So these 4, this is kind of a collection of what all that Elios has done for us. And starting from your viewer's left, this is a shot of the actual flight in the bin during our November mission to collect the LiDAR data, and then a representation moving to the next image, the LiDAR map. Now, this image to the right is actually pulled from Inspector software, and the Inspector software is a huge part of the benefit that comes with the Elios drone. It provides rapid review of the mission you just flew in a very intuitive sense. So you get a view of your LiDAR map, you get a view of where the drone is inside that LiDAR 3D map, as well as you get visuals from the camera at the same time. So it was very helpful to know exactly what you're looking at, quickly find areas of interest, and review those areas of interest once you've flown your mission. Further, moving to your right, there's actually a photogrammetry image. This was when we were looking at Elios 2 before the Elios 3 was released. So we thought we would be building our map using photogrammetry. And so this was a map we built from one of our mock-up facility. We have a mock-up of one of the bins, and we did a test with the photogrammetry. As it turns out, on the far right, that is an image of one of our facilities out there in Idaho. One of the things we've been using the Elios 3 for when we're not flying in high radiation areas is to create digital twins of our facilities. This is something that the Department of Energy is interested in moving forward on, and it has great benefits for doing facility upgrades or doing any kind of facility walk down. You can save time once you've developed your digital twin. There's less need to actually go out to the facility if you have to evaluate a certain area of the facility. You have an excellent digital twin of your facility. So we're doing a lot with the Elios 3 in that regards. So those are the 4 photos.
Thank you very much, Kevin. I'll swap over so that we're just looking at my questions screen so people can see where to go if they have questions. So the follow-up question, well, not follow-up, but a separate question is, what relative accuracies did we achieve on the 3D point cloud, and how did we verify it?
That is a really good question. We did some initial verification on the point cloud by taking, for instance, we do know the dimensions of the bins, right? So we know the cross-sectional dimensions of the bins, and so we did some checks on that cross-section with the LiDAR point cloud versus what the dimensional drawings indicated, and there were certain areas that were sub-centimeter accuracy, and others that were not as accurate as that. So I don't have an average, but I know we did achieve certain data points that were sub-centimeter. And the bottom line for us was that we were able to get enough accuracy on all of the obstructions within the vault where we can move forward, our engineers can move forward with planning exactly where to drill holes in the concrete roof of the vault and lower our retrieval equipment, our robotic retrieval equipment down that will robotically cut into the bins and retrieve the equipment. So that was our primary goal, and the accuracy that we achieved with the Elios 3 LiDAR was appropriate for that use.
All right, great. A follow-up question, and it's quite a good general question for the drone, is how did we communicate with the drone? As in, was it direct? Were there any repeaters, etc.?
Right. Nope, that was a good one. In the video that we showed right up front, as the drone was flying down into the hatch, one of the things we did as soon as we opened the concrete hatches, the hatch openings are huge concrete blocks that have to be lifted out with a crane. Once we had both of those hatch openings open, we lowered into the vault a range extender antenna, which is something that Flyability provides as an option for the Elios 3. And essentially it is an antenna with some amplification circuitry that is at the end of a long cable. So since our vault was underground and our pilots, of course, were above ground, several meters away from the opening, there was a large amount of earth between us and the drone. We absolutely felt that the range extender was an essential piece to ensure we maintain very solid communication with the drone as it was flying inside the vault. And we had no problems at all in that configuration with any dropouts, any video dropouts. It was a very solid performance with the range extender antenna.
Okay, great. We've got questions coming fast now, so there's lots to cover. So we had one question, which was actually a question I had for you the first time we talked about it, which was understanding that the drone was left in the vault. What would there be a potential way to get it out, or is there a potential plan to get it out, like with a cable or something like that?
Absolutely. No, this is something we discussed immediately after it was lost in the drone, or lost in the vault, you know, where the battery finally died, and said, well, it's down there. The hatch, these large concrete hatches are still out. We kind of had a quick discussion with our operations manager, our safety manager, and then our project manager, and said, do we want to attempt to literally lower a line with a grappling hook to hook the cage and see if we could pull it out? Because luckily the drone landed on top of the bin, very close to beneath the hatch opening, and it did not go all the way to the bottom of the bin. That would have been much harder to retrieve. But the point here is the safety manager said, this is not listed in your work procedure. You will not do this until we have proper work procedure to establish this. And there's some security and safety issues with leaving the concrete lid off the vault for too long. So they put the concrete lid back on the vault. Everyone said, okay, it's not going to hurt anything. We got our data out. We'll leave the drone down there. And then next time they open the concrete hatch to do their general inspection, they said at that time you can have your paperwork ready to go and attempt to retrieve that. So that won't be for another, I believe, another 3 or 4 months. So I'm hoping that we get the chance to retrieve it. Being an engineer, I love data. I would love to see how the lenses on the cameras hold up to the radiation. A lot of times lenses will cloud or turn brown due to radiation, as well as just any of the other materials, and see how they have held up with constant 700 RAD or 7 gray per hour field.
Well, if it goes well, we'd love to talk about it in the webinar, in another webinar.
I let you know.
Okay, great. There's been a question, which is, can the Elios 3 RAD measure radiation in the air in terms of airborne contamination? I think that's probably a better question for Jeff, if you're here. Right, taking him a second. There we go.
So the radiation sensor can only measure gamma and beta radiation. So I'm not sure if this would qualify to measure radioactive dust that may deposit on the drone itself.
Okay, perfect. Thank you very much. Just going through some more of our questions. Jeff, actually, while we have you, another question. How are the electronic components of the drone protected from the radiation?
So we did quite some work to make the electronics as robust as possible. And actually, Kevin did a very thorough assessment on how radiation rugged the drone is. Maybe Kevin, you want to touch base on this?
Sure, you're right. We, you understand, most methods for making an electrical device radiation tolerant involves adding shielding of tungsten. It used to be lead, but primarily tungsten now, which is a very heavy material, which is what you need to protect for radiation. That does not work well on drones, inspection drones. Any amount of weight cuts into your flight time, and there are plenty of other trade-offs, as Jeff and the rest of the flyability team are aware of in terms of weight and flight time. But so we knew that there was not intentional shielding applied to the Elios 3. What we wanted to do was just to see how tolerant the systems on the Elios 3 were. When we did our testing in front of the high-powered X-ray generator down at Idaho State University, it was basically to see, as a commercial product, how does it survive the radiation fields. And we were very happy to see that even without shielding, the camera system performed well, the LiDAR system performed well, the transmission system performed well. As I mentioned, when it finally failed after roughly 40 gray or 4,000 rad of cumulative dose, it was actually the memory card that is associated with the onboard computer would not allow us to re-initialize for another flight. So I would like, as I had mentioned earlier, I would love to do, and I'm in contact with some other engineers at Sandia National Laboratory in New Mexico to see if we can do a more extensive radiation tolerance test with multiple Elios 3s. I would like to do a minimum of 5 tests to failure to get a much more confidence level as to what the maximum dose rate as well as the maximum cumulative dose that an Elios 3 can survive. For most cases, what we found, it's good enough for many of our missions in the waste remediation world.
That's great. Thank you, Kevin. I'll be interested to see the results of more testing to failure, although I feel a little sorry for the drones.
We're working on approval for that one, yes. It costs a little bit of money.
Yeah. Actually, so you mentioned something to do with X-ray as well. So I've got a question that's a little bit more generalized, and basically, how is this helpful in personal dosimetry inside premises of radiation workers or patients in care of hospitals or treated with active radiation?
Would you like me to answer that one?
I think so. And Jeff, if you have anything to add, you can jump in after Kevin.
Well, I certainly can talk about in the nuclear waste remediation world, there are many instances where we have radiation workers, we call them RAD workers, that are trained to minimize their dose when they go into a lower radiation level. Now, that area in the vault where we sent the drone, we would never send a human being. It's way too high in radiation. But there are plenty of other areas where we know a worker will go in to do a particular job, and they may receive, 4 or 5 millirem of dose, and that's an acceptable trade-off to get the work done. We know that, but the goal is always to do what we call ALARA, or as low as reasonably achievable in terms of dose rate. So when you have this opportunity to send in a drone to do an inspection that normally you would send a human being in, even if you're saving an exposure of 4 or 5 millirem, the Department of Energy in their ALARA principle says that you should always use the technology before you have to send a human in. And that's what makes this indoor inspection drone technology such a valuable tool for the waste remediation world, as well as the commercial nuclear world, I would imagine. Once again, I work more in the waste remediation world where we're cleaning up older sites. But that is where it is very valuable for RAD workers, so that they do not have to receive an unnecessary dose of radiation.
Great, thank you very much. So I think we're only going to have time for 1 or 2 more questions. So the next question is, with regards to dust, did that make it a problem to take photos in that area? And before the mission, did you expect to decontaminate the drone at the end of the mission to use it on other sites?
very quickly, I'll answer both of those because we considered both of those. The first one about the dust and being able to image, flyability engineers already took care of that one with some amazing oblique lighting capability on the drone, so that it's the lighting is not reflecting right back into the lens of the camera off of the dust particles, and it's amazing how that really helps in terms of your image quality. So the lighting on the drone already takes care of that. It's designed to take good imagery in high dust environments. Now, as far as contamination goes, yes, we took precautions as the drone came out. We put a tent around the opening of the hatch that had actually like glove box access. So our radiation specialists, as soon as the drone came out, they took swipes off of the drone in several locations. They tested the swipes to see if there was any radioactive dust on the drone, and there was not. So all of the dust, all of the radioactive material was still contained inside the bin. There was no contamination, no radiation contamination that had gotten out of the bin and then onto the drone. But definitely, if you have radioactive contamination in an area, you have to evaluate the use of an indoor drone very carefully because of the amount of prop wash and the movement of that radioactive material based on the flight of the drone. That has to be something that is evaluated carefully before you do that mission.
Okay, great. And then I think this was the final question. Did the LiDAR continue to work correctly after 40 G of dose?
Yes, it did. It was chugging along perfectly fine. In fact, every system, with the exception of the onboard computer memory card, was still operating very well. So if there is a way to put a better an SD card or a memory card that is more radiation tolerant just due to the inherent design of the circuitry, you may be able to see even higher levels of tolerance, radiation tolerance on the drone. That being said, this is why I want to do additional testing with additional Elios 3s, just to make sure that our one case study was not an anomaly in any way.
Okay, great. Okay, I'm going to do one last question because we still got 1 or 2 more minutes. How accurate are measurements that are and what is the range for the measurement? So like, what's the low limit for background?
Jeffrey, do you have a better answer on that one?
Yes, so I believe the sensor goes down to 0.3 micro up to 10 sieverts, and the accuracy is couple of percent. So we are within all the requirements in terms of radio protection for this kind of radiation detection device.
Great. All right. I think that's all the questions we have time for. If we've got any more, I will make sure we get in touch with you, but I think that's all. Thank you all very much for your time, and thank you, Kevin and Jeff, as well. For those of you that have attended, you should receive a recording of the webinar within the next couple of days. And if you have any more questions, you can reach us at communication@flyability.com. So yes, thank you all very much for your time, and have a great day / evening, depending where you are in the world.
Thank you.
All right. Bye now.